everybody, welcome. Today's lecture is about acid-base balance. Okay, so this has to do with the pH in your body. Remember that pH is something that is homeostatically controlled. So we're going to look at today at how we do control the pH within our body. Remember, pH is really important because pH can denature our enzymes as well as other proteins in the body. So we have to keep a very steady pH within our blood and other areas of the body. Okay, so just a little background on pH to remember. pH is a term we use, means potential hydrogen, to express the concentration of hydrogen ions. I'm losing my voice already. All right, so again, it's a way to express the levels of hydrogen ions. The more hydrogen ions you have in the body, the more acidic it becomes, right? And so remember that hydrogen ions, it can come from splitting of water, H2O. So when water splits into a hydrogen ion, right, and it leaves the electron behind with the other portion, the OH. Those are the hydroxide ions, OH negative. Okay, so pH is really the proportion of hydrogen ions to hydroxide ions, right? So the lower the number, it means the more acidic that the pH is, okay? So a low pH means high acidity, okay? 7 is about neutral. You can see here, let me get my laser pointer out. You can see here right in the middle of our pH scale is 7. That means it's pure water. That means the number of hydrogen ions balance the concentration of hydroxyl ions. So those would bind together and you would get H2O. Okay. So again, anything less, any number lower means there are more hydrogen ions. So the concentration of hydrogen ions goes up as we go lower on the pH scale. So hydrochloric acid is one that is extremely acidic, a pH of near 0. Okay. On the other scale, that means we get more hydroxyl ions and less hydrogen ions. So that means the number is going up. And so the greater the number over 7, the more basic it is, or the more alkaline it is. Okay, so it's important to remember sometimes this gets confusing because the pH scale seems to be opposite regarding the number of hydrogen ions, the concentration of that. But I'm not going to make you guys learn this, but what the equation to actually determine pH is actually, it's defined as the negative logarithm of the hydrogen ion concentration. So because it's the negative logarithm, then the fewer or the more hydrogen ions will be a lower number. Okay, if you want to go through the math later, we can do that. You can come see me in office hours, but I won't make you do that for the class, so I'm not going to put it here. But it is important to not get confused when you see somebody says it's high acidity, right? If they're referring though to the pH number, it's going to be a low number. It's going to be between 0 and 6.9. Okay, if it's alkaline, right, then you will see a higher number. Okay, so again, very important to remember that. Okay, here's another view of the pH scale and how it pertains to us. So normal blood pH is 7.35 to 7.45 in humans. Okay, so that's the range, that's what we homeostatically control. So we can tolerate this range in between 3.75 and 3.45. When we start to get just below that, we get into a condition called acidosis. Okay, when we start to get above it, we're into a condition called alkalosis. Okay, so we have to keep our pH especially above 6.8. Okay, so if our arterial pH is below 6.8, death can actually occur even after just a few seconds of falling below 6.8. Or even death can occur if we fall out of range above 8.0. Okay? So because of that, we really highly regulate the concentration of hydrogen ions. Okay, so the consequences, if we have fluctuations in pH, then again, the clinical effect of acidosis, this can really affect your nerves. A depression of the central nervous system. You can get disorientation and you can die from a state of coma. Okay, and alkalosis, or again, a decrease in the hydrogen ion concentration, you can get an overexcitability of the nervous system. So first in the peripheral nervous system and then in the central nervous system. So some of the first feelings of being in alkalosis, feelings of pins and needles, you can get muscle twitches, spasms, right? Another thing, so our kidney, we're going to see how we regulate hydrogen ions. And our kidney is one of the organs that we'll look at that can do that. Okay, and I think I had mentioned before in the kidney lecture that we secrete potassium from the kidney, but when you have an increased hydrogen secretion, then you'll get a decrease in potassium secretion and vice versa. So that can actually change the extracellular fluid levels of potassium, which could then cause cardiac abnormalities and things like that, right? So again, by not controlling hydrogen or having to deal with hydrogen, then that can have kind of a cascade effect into other things. Okay, so sources of hydrogen ions in the body, we already saw carbonic acid formation. Remember that we produce carbon dioxide and our body is mainly water, so we can actually form carbonic acid. Other things such as inorganic acids produce during the breakdown of nutrients, organic acids that result from intermediary metabolism. So there can be a lot of sources. So again, we have to look at how we tightly control this. So again, normal blood pH 7.35 to 7.45. That's the range that we homeostatically control pH in. Okay. This is just another picture of the pH scale if you like this one. So here it's showing the entire pH scale from 0 to 14, and that neutral is 7, and that our blood pH is 7.35 to 7.45, right? So that's the average. We're just a little bit on the side of basic, right? But even, again, the wide range is what, if you fall out of acidosis, then death can occur. And you can just see how narrow that range is on the pH scale. So really important, this concept of controlling pH. Okay. So our defenses against pH, we have two main lines of defense. We have a chemical buffer system and then physiological buffers. Okay, so chemical buffer systems, some of these we have seen already. That's the first line of defense. So when pH is starting to either go too low or too high, chemical buffer systems tend to kick in. And actually, we maintain chemical buffer systems. Remember that when we release CO2 from our cells, the red blood cells can pick it up and then convert the CO2 into hydrochloric acid. I'm sorry. I'm thinking of digestion, I'm sorry. It'll convert the CO2 and water into carbonic acid and then split that and release the bicarbonate, there we go, the bicarbonate into the bloodstream, right? And the hemoglobin can hang on to the hydrogen. So that bicarbonate traveling into the bloodstream, this is the bicarbonate buffer system, then it can pick up any of these errant hydrogens that are roaming around in the blood or as it goes by the tissue, right? So again, it can pick up and it can even release the hydrogens. If it's already holding on to a hydrogen, it can release the hydrogens if we're going more alkalosis, right? To the alkaline area. So carbonic acid is mainly in the extracellular fluid, and buffer changes can be brought on by other things other than carbon dioxide, like lactic acid. That's a way for free hydrogen ions to get released also into the ECF. Okay, protein buffer system. This mainly occurs in our intracellular fluid in the ICF. So proteins, remember there's proteins inside of our cells, and they contain both acidic and basic groups that can give up or take up hydrogen as needed. So within the cells, they have this automatic buffer system. Okay, and then the phosphate buffer system. Phosphates are most abundant inside of the cell, and so it's a good intracellular buffer. Okay, it ends up being a urinary buffer as well because we tend to consume more phosphate than is actually needed. And so it ends up getting filtered by the kidney for excretion. So it can actually buffer the urine itself. Okay, so those are the main chemical buffer systems. Then as we get into the physiological buffers, so again, the chemical is the first line of defense. The second line of defense against changes in the pH is our respiratory system. This kind of acts as a moderate speed, right? Compared to the chemical, that's always happening. These chemical reactions are happening all the time. So the respiratory system is acting more at a moderate speed, right? And again, it's going to regulate the pH by controlling the carbon dioxide removal, either by increasing your respiratory rate or decreasing it as needed, right? So at normal pH of about 7.4, the ventilation rate is normal, the rate of CO2 is normal, the rate of carbonic acid formation is normal, and the rate of hydrogen generation from carbon dioxide is normal. But then as you get into acidosis, when your pH begins to fall, look, we're at 7.1 here. Okay, so that is outside of normal range. Remember, the lower range of normal is 7.35. So this means that you're holding on to carbon dioxide. So you're going to increase your rate of ventilation. If you increase your rate of ventilation, you're losing more carbon dioxide. That's what you need to do, right? Because therefore, when you lose more carbon dioxide, then you're reducing the amount of the carbonic acid formation, and you're reducing the rate of the hydrogen generation from carbon dioxide, right? But if you go the other direction, you go above 7.45 and you reach that alkalosis, then the automatic, right, your brain will automatically kick in from the medulla oblongata to slow your ventilation rate down. And then that causes you to hold on to CO2 into your blood, okay, because you're not expiring it out as quickly. So therefore, you increase the rate of carbonic acid, because we want this to go lower, right, your pH number. And then therefore you increase the rate of hydrogen ion generation. Remember, we need more hydrogen ions in order to get away from alkalosis and back into normal range. Okay, so that's the respiratory system. So the third line of defense then are the kidneys. Okay, so the kidneys can defend against a change of ion concentration as well by excreting hydrogen out of the blood. So we do have that ability down at that distal tubule to secrete hydrogen from the blood into the distal tubule, which will then go into the urine and get excreted out of the body, right? And then remember that at the kidney, we filter bicarbonate as well. And so if we're too alkaline, then we can excrete that bicarbonate out of the body as well. Okay. We can also secrete ammonia. Ammonia can become toxic very quickly, and so we may want to excrete ammonia out of the body. So all of these things really help to control the pH. So again, the kidneys will kick in and do that if necessary. So again, the chemical changes, the chemical reactions are just constantly occurring within our body, and we've been through many of those. We saw those. Okay, but then the next line of defense, our respiratory system will make adjustments. And if it's still long-term, we're either more acidic or more alkaline, then the kidneys can kind of make adjustments through the excretion in the urine. Okay. So acid-base imbalances, they arise usually either from respiratory dysfunction or from disturbances in metabolism. So when the cells are doing work, there may be some disturbances in there. And so we end up calling that, putting it in 4 categories. So if it's called from respiration, then it depends on, is it acidosis or alkalosis, right? If it's from our chemical reactions in our cells, then that's metabolic, again, whether it's acidosis or alkalosis, as the case may be. So here are some case examples. So again, respiratory acidosis results from the abnormal carbon dioxide retention, usually arising from hypoventilation, right? So if for some reason you're not breathing normally, you're breathing at a lowered rate than normal, this guy's saying here, I can't catch my breath. Again, that means your lungs are retaining the carbon dioxide levels, right? So the pressure goes up in there. So if you are retaining carbon dioxide levels at your plasma, then your pH in your blood is going to go down. That means it becomes more acidic, okay? How does this happen? It could be lung disease. It could be if there are any drugs that are being taken, and again, it could be over the counter or not, but that could depress the respiratory center in the brain. Sometimes nerve or muscle disorders can reduce respiratory muscle activity, right? So if it's affecting your diaphragm, that's going to affect the rate of respiration. Again, if you slow it down, you're going to retain the CO2, right? So how do we compensate for it? There are chemical buffers. Again, remember, chemical usually starts first. They immediately take up the hydrogen. But usually then this becomes a long-term problem, and the kidneys end up being the most important in compensating for respiratory acidosis because it skips that second step of respiration, right? The respiratory system is unable to control it. So then the kidneys end up kicking in. Okay. Respiratory alkalosis. So this is the opposite now. It's primarily due to the excessive loss of CO2 from the body. And that's usually due to hyperventilation, right? And again, you can read these slides and see some of the causes and the responses, the symptoms of respiratory alkalosis, right? So what could cause this excessive loss of CO2 from the body due to hyperventilation? Sometimes fever, if somebody is excessively anxious, right? Aspirin, taking too much aspirin, you can get aspirin poisoning, could cause this. If you spend a lot of time at high altitude, right, that can also cause excessive loss of CO2 because you're trying to breathe more quickly to get more oxygen in. Well, you release more CO2, right? So again, you get a loss of CO2, an increased loss of CO2 in the lungs, right? So when you lose CO2 out of the blood, your pH climbs, and that leads us to alkalosis, okay? Again, chemical buffer systems are constantly working, but if the situation continues, since again, the respiratory system isn't functioning correctly, it's the kidneys again compensating by conserving hydrogen ions in the blood, but end up excreting more bicarbonate ions. Okay. So let's get into the metabolic reasons. So here's metabolic acidosis. So this is all the other types of acidosis caused by anything other than the CO2, right? Other than the relationship with the lungs, right? So what can cause this? Severe diarrhea, right? Diabetes mellitus can cause metabolic acidosis, and many times metabolic acidosis is the precursor to diabetes, right? Strenuous exercise, uremic acidosis. So if the kidney isn't functioning correctly, that's uremic acidosis. Okay, so compensations, again, buffers will end up taking up the extra hydrogen because it's acidosis, so there's extra hydrogen ions. The lungs can end up blowing off additional CO2, which then balances out that carbon dioxide or carbonic acid, right? And then again, the kidneys can secrete more hydrogen and conserve more of the bicarbonate, right? So again, you want to get rid of hydrogen ions and maintain more of the bicarbonate, right? And acidosis. Metabolic alkalosis, it's a reduction of the concentration of hydrogen ions in the plasma by relative deficiency of non-carbonic acids, right? So what can cause this? You can see they're holding their mouth, nausea, vomiting, right? Ingestion of drugs that are alkaline. So again, now the chemical buffer systems will immediately release hydrogen ions because we're alkalosis. We balance it out by putting in more hydrogen ions. Okay. If the condition persists for several days, then the kidney will end up conserving hydrogen ions and excreting the extra bicarbonate ions through the urine. Okay, that's it for balancing our pH. This was a short and sweet lecture, but it's a very important topic. All right, thanks guys. So hopefully what you saw is that we learned some of this already and we're just kind of tying it all together. All right, thanks everybody.